It's really my pleasure to announce the first plenary speaker of the day, Professor Barbara Kaltenbacher. She is an Austrian mathematician. She studied and got her PhD at the University of Linz in 1996. Then she got some positions in Germany, first at the University of Erlangen, Nuremberg, then in Göttingen, and finally she became professor in Stuttgart. In 2010, she moved back to Austria, first at the University of Graz, and after that, after 1 year and a half, more or less, she moved to the University of Klagenfurt, where she is now. Among her remarkable recognitions, she has been chair of the Weinstrass Institute in Berlin. She is also a corresponding member of the Austrian Academy of Sciences, and she was for 3 years president of the Austrian Mathematical Society. Her topics of interest in mathematics range over several topics, among which PDE constrained optimization, inverse problems, fractional PDEs, and today she will combine inverse problems and fractional PDEs in her talk, whose title is Some Inverse Problems for Fractional PDEs. Barbara, you have the floor.
Thanks a lot for your kind introduction, and let me thank the organizers and the steering committee of this conference and this conference series for the great pleasure and honor that I have to give a talk here. I hope to convince you that inverse problems are an interesting topic. Many of you might already know that, of course. And that it's worth also looking at this from the mathematical perspective that you in particular have. So the work that I'm going to talk about is joint work with William Rundell from Texas A&M University, with whom I have written a book recently on that topic. It's called Inverse Problems for Fractional PDEs, and I was asked to talk about this topic. Then when setting up the talk, I thought to myself, it's just simply too much, so I added the word some inverse problems, and in particular it will be two of them that I will focus on. So starting off to dwell a bit on each of these words in the title, let me start with inverse problems. So inverse problems are, very generally speaking, concerned with determining causes for either observed or desired effects. This is mathematically actually close to each other, so in the sense of determining, but there's actually two fields that this definition covers, the field of optimization and the field of inverse problems per se, where one wants to identify some unknown quantity from given observations. And some typical features of inverse problems are as follows. First of all, they tend to be unstable, as you will see in the example that I will, in one of the examples, very unstable even. So this means that if we have observations, so these effects that we observe, and we do measurements, then usually there's a measurement error that one makes, and as a consequence of this instability, it could be that with naive approaches that one gets complete garbage when trying to reconstruct from noisy data. So that's why the field of regularization methods, regularization theory, is quite important to the field of inverse problems. Next item, since we are looking at identification problems, it's important to make sure that the effects, that the observations that we take are really sufficient to uniquely determine what we want to identify. So the question of uniqueness also plays a major role here. Actually, I have to confess I have prepared two proofs for this talk because I really like to show proofs in talks, but well, let's see what works out. One in the sense of regularization and one uniqueness proof. On top of this, of course, right now, this is a very general statement here. What is in between the causes and effects, that's also an important field for mathematics, namely modeling. Yes, the connection between causes and effects, that's usually a model, and it's quite often a PDE or ODE model. So it's about modeling the underlying physical, biological, economical, and so on and so forth, laws in a mathematical language, and well, my co-author would say the lingua franca of science is PDEs. I subscribe to that. Okay, so the simple picture of this is that looking at inverse problem, we first of all have a forward problem in mind. So that's the PDE with boundary conditions and so on and so forth. So usually what is considered in PDE analysis and numerics. So that's the connection between cause and effect, usually called forward problem. Well, and the inverse problem tries or aims at inverting, as the name tells, instead of looking at the map from cause to effect, to look backwards on the mapping or on methods to reconstruct the cause from the effect. So what could be a cause, under quotation marks, what could be a quantity of interest that we want to recover? Quite often in the context of PDE models, it's coefficients in this PDE, namely not just constants, but space-dependent or time-dependent coefficients. If it's about space-dependent coefficients, it's quite often about imaging with mathematical models. It's also quite often initial conditions, and actually the two examples that I'm going to show will be about recovering initial conditions. Also the boundary of the domain where the PDE holds might contain some unknowns, or might actually even itself be unknown, so then it's about the shape, a geometry that needs to be recovered, or also in the context of PDE, source terms are quite often of interest. So what's the typical data that is available? Well, when really looking at tomography, so mathematical imaging, then it will be data on the boundary of the domain where the PDE holds. So boundary traces, single boundary traces, or multiple, infinitely many boundary values. That's typically called the Dirichlet to Neumann map. So that's the map, the full map that takes arbitrary Dirichlet boundary values to Neumann boundary values. That's a typical instance of such a boundary observation. Also far field, of course, far fields in inverse scattering are a prominent example here. Okay, just to have something in mind in the general setting, but I will very soon specify. So what I have in mind is coefficient identification in, for example, elliptic PDEs, where these coefficients A, B, and C themselves, beside the solution U itself, might depend on X. Okay, thereby giving a means to do imaging by means of these inverse problems. And then we have boundary conditions. For example, we have a Neumann trace, or actually many Neumann traces, or maybe even the complete Neumann to Dirichlet map, the other way around. So this has many applications, clearly. I mentioned one already, medical imaging. There's a classical inverse problem that I should mention here, electrical impedance tomography, which is classical not only from the application point of view, but also from all the mathematics, the beautiful mathematics that is behind this, which would be setting C and B to 0 and just looking for A, which is the conductivity, a distributed conductivity, or its reciprocal would be the impedance, name giving in this problem here. And then one would not just have one observation, but infinitely many on the boundary in order to uniquely recover A of X. So same thing can be done for non-destructive testing. There's also, of course, seismic prospection, material characterizations, all kinds of things. not only engineering, which is sort of dominant here, but also biology, economy, and so on and so forth. So in this talk, I will look at time-dependent problems. So I could simply add a time derivative, first or second time derivative, or fractional time derivative, of course, to make this time-dependent. I'm going to formulate this in a more general way. So we have something like a state space system. So you have an evolutionary problem given by this abstract ODE, which can be a PDE if the object u of t is in a function space itself, equipped with initial data and depending on a parameter theta. And by the way, also the initial data might depend on that parameter, or the parameter itself might be the initial data. So the green object is here the one that is to be identified, and the observations are ideally observations over time, very ideally full observations, a bit more realistically indirect observations formulated by this G over here, or even more realistically formulated not continuously over time, but just at discrete time instances. And this has applications clearly in population dynamics, epidemiology, so biological applications. Also combustion is something which we looked at in such a context. So that's typically the parabolic version. But of course, this system can also model waves. If you write it as a first order reformulation of a second order wave equation, or first order conservation laws. And then it's about imaging with waves, which is also something which is quite important in applications. So here are the two instances that I would like to look at more closely with you today. And they are both examples of problems where one wants to recover the initial condition of the state. So U is the state here, the solution of the PDE. We want to recover the initial condition, so U at time t equal to 0. And what we have available are observations at final time. So we want to go backwards in time. Underlying is a diffusion process, and of course you might all guess or already know that this is severely ill-posed, because the diffusion process is infinitely smoothing, which means that every detail that we might want to find in U0 is immediately smeared out. Okay, so that's a severely exponentially ill-posed problem. We will see this in the formula a bit in a moment. Another related problem, very much related actually, is photoacoustic tomography. So I will say a few words more about what it actually is, if time permits, but mathematically speaking, it's very similar to that one, just it's a wave type problem, because clearly it's about acoustics. It's recovering the initial condition, one of the initial conditions, because we have a second order wave equation, from later data. So in this case, it's not final time data, because doing final time data like this would mean that we would be able to look into the domain that we want to image, which is not the case, so it's boundary values that we can observe. But to make up for the missing dimension, instead of the three-dimensional x in omega, we have a two-dimensional x on the boundary plus the timeline. Okay, so in terms of dimensionality, it works out in principle to recover the U0 here as a function of x. The d over here is a damping term, and here's one place where fractional derivatives will come into place. The second place will be over here, replacing ut by a fractional derivative. So, and actually if the damping term is just 0, if you just have a lossless wave equation, lossless wave propagation, then it's clear from, if you think of 1D D'Alembert's formula, that U0 can be uniquely recovered without any losses. So it's just a formula in 1D that we have to evaluate. and it's similar in higher dimensions. So the inverse problem of recovering U0 without damping is at most mildly ill-posed. In certain situations, even well-posed. Okay, this is still the case if the damping is weak. Weak in the sense that there are no very high derivatives. So weak damping, as it's called sometimes, would be to put ut here. But quite often one sees the strong damping term, this one here. And this strong damping term, if you imagine minus Laplace ut here, you have a strongly damped wave equation. And this actually exhibits parabolic behavior in the sense that it enjoys maximal parabolic regularity. It gives rise to an analytic semigroup, and one can show exponential decay of solutions. As a consequence, the behavior of the inverse problem is similar to that of the backwards heat equation, namely exponentially ill-posed with the strong damping. And mathematically speaking, replacing this strong damping with fractional damping, one would explore, so to say, the space between weak and strong damping and see what the consequence on ill-posedness will be. But there's also here an important modeling component, which I would also like to point out here. One more thing that is common to both of them, because it's about problems going backward in time. If you apply conventional regularization methods, such as Tikhonov regularization that you might be familiar to you, causality, so the going forwards in time, is lost, which is of course intuitive because we do want to go backwards in time. We want to conclude from this final time to the initial time. But in Tikhonov and alike, this is really a very strong coupling which sort of destroys the mathematical structure that one would like to use in such problems. So looking at methods that preserve the temporal causality to some extent will also be a topic of this talk. Before going there, next, so yes, this was, at the beginning it was inverse problems, then we had some PDEs, and this slide stands for the word sum, because it will be two of them, okay? Now fractional. So fractional derivatives have been known for a long time. That's why I like to attach the name Abel to them. And they start off with this fractional integral operator. So that's the ordinary integral operator with a singularity that can be scaled, so to speak, by this exponent. And it corresponds to, so alpha equal to 1 corresponds to just integration, alpha equal to 0 up to initial values corresponds to the identity, basically. And then in order to build a fractional derivative, and it will be a fractional time derivative in this talk, one can choose to either apply the integer time derivative after doing this fractional integration. So then this 1 and this single d by dt cancels out, and it will be, so to speak, an inverse to the minus alpha integration, which is then alpha plus differentiation. Or one can do it the other way around, again with this cancellation, but first differentiating and then doing the integration. So the latter is the one that is, of course, applies to a smaller class of functions, because they have to be in some sense differentiable in order to apply the derivative to them as compared to the upper one. But imposing initial conditions is a bit tricky with the Riemann-Liouville derivative, because the reason for that is that constants, if you do a fractional Riemann-Liouville derivative, if you apply this to a constant function, the outcome is not 0. The outcome is actually a function exhibiting a singularity at 0. And that's not very natural. At least it's not very useful when applying this in physical context where one wants to impose initial conditions. And in particular, if you want to recover initial conditions, that plays an important role. So it's actually this DC, Chebyshev-Caputo derivative that we will look at in this talk. And here's the time to point to some recent books on fractional PDEs. That's a non-exhaustive list, but it's sort of my favorite reading list. Well, at least two of them. Namely, of course, in the context of inverse problems for fractional PDEs, there's a really important name, namely Masahiro Yamamoto, together with many co-authors, whom I would like to give reference to, who has written a really nice book together with two co-authors, and actually one of them is here at this conference, which is really nice, Katarzyna Rzycewska. I don't know whether she's still here, but I saw her yesterday in the session. There's also a really nice book on also fractional PDEs, but in particular also numerics of fractional PDEs, written by Bang-Thi Yin in 2021. There's a follow-up book by him and a co-author, which I also would like to recommend. Yes, and that's this book that I mentioned, which we wrote with Bill. Okay, but let me point out in the context of this fractional integral operator here that it's a non-local operator, non-local in time, in the sense that for computing the derivative at a time instance t, it requires clearly the values of the function to be differentiated not only at t but also at previous values. So it's non-local and in a causal way. And of course, due to the singularity, the current time instance t is given the most emphasis in this integral, which makes a lot of sense, but still backwards values are kept in mind in the sense of a memory, and this is good for reconstructing initial conditions, because if we have a PDE or ODE that keeps their initial values in mind, then it's of course more easy to reconstruct these initial values. And we will actually see this. So another object of interest is this class of functions, the Mittag-Leffler functions. They play an important role in the context of, first of all, fractional ODEs, but via separation of variables also PDEs. And it's defined like this. You might have seen it already. So it's defined by a power series, and it can be viewed as an extension of the exponential function. And actually, we are going to use it as such. If you look at alpha and beta here and put both of them to 1, then you have gamma, the gamma function of k plus 1 here, that's k factorial, and you end up with the exponential series. Okay, so this function has been intensively investigated. Here also some references. And one important property of this function that we are going to make use of, we're going to use more of them, is the fact that it satisfies this fractional ODE. So that's the important thing here. So it's, so to speak, an eigenfunction of this fractional time derivative here. Not the Mittag-Leffler function itself, but with an argument, with a negative argument, this will be important, involving this lambda here, this, if you want to call it eigenvalue, this eigenvalue lambda here, and some certain power of the time. Okay, and a thick minus here. Okay, now we are ready to start. Let me have a look at how much time is left. Oh, okay, I have to, it's as always. But yes, I will try my best. Okay, there's these two problems here. That's the backwards diffusion equation and its regularization by replacing the time derivative by a fractional one. That's the first one. And the second one is photoacoustic tomography with fractional attenuation. And if time permits, which for sure will not be the case, I'm sorry, I thought about showing you some further inverse problems for fractional PDEs, but yes, let's see. Okay, starting off with the backwards heat equation. I mentioned that Tikhonov or any conventional regularization scheme would remove causality, which is not desirable, but there's a nice class of, actually nice concept called quasi-reversibility, which was discovered in, well, not far into the second half of the last century, so also quite some time ago, and which we rediscovered in the context of fractional derivatives. So the problem looks like this. So that's our backwards heat equation with a slightly more general elliptic second order differential operator L here. So you could imagine just a Laplacian here with initial conditions. And then we have final time values, and we want to recover U0 as a function of x. Sorry, there should be an x also over here. So for the moment, L is uniformly elliptic, symmetric, and so it's a simple object. So one can also generalize this to the non-symmetric case, but that's not subject of this talk. And also the domain is supposed to be sufficiently smooth. And so why did we look at this problem? First of all, we already had this photoacoustics problem in mind, and we had in mind that going backwards in time is something of interest here. But first of all, usually one looks at model problems, and this serves as a model problem for many other things too. And actually one of the important applications is recovery of sources for contaminants. In that case, actually the operator L will be non-symmetric because it will involve some transport as well. Well, the other motivation you have seen, that's imaging with acoustic waves or also elastic waves with strong attenuation, because also then the problem behaves like a parabolic one. And well, going back to just the Laplace operator up here, then if you solve this by means of the Green's function, then you have, then it's equivalent to a blurring. So applying the forward operator is just blurring. It's a often used model for blurring images. And then doing the inverse problems would amount to deblurring, also something which occurs quite often. So quasi-reversibility, what does this mean? So we start off with this problem. That's actually what we want to solve. No fractional derivative or anything involved. But the concept of quasi-reversibility amounts to replacing the forward problem by something which is more amenable to inversion. So we have seen previously that, for example, if you replaced this parabolic problem by a hyperbolic problem, an undamped one, it becomes well-posed. And that's actually what people have been doing already a long time ago. So that's what you see here. It's just adding a second time derivative. Of course, one cannot just add it. One has to make it small in order not to perturb the original problem too much. But doing this, exactly this, ut just becomes a weak damping term instead of the dominating one, and then for strictly positive epsilon, this becomes a well-posed or at least just mildly ill-posed problem. One can also play with the space derivative, just taking the squared Laplacian here with a small epsilon, and also this becomes a well-posed problem. So another instance is this one here, investigated by Ralph Schowalter, which might look familiar to you because it's actually the regularization that is contained in the proof of the Healy-Phillips-Yosida theorem. And it's used really for regularizing this backwards inverse problem. There's another way of doing it by, so looking back up here, by adding a tiny little bit of U0 up here, of the unknown U0 in the final condition. That's what is done here. And That's also a nice idea, I find. However, it's again going back to this paradigm where it's not causality preserving because the initial condition pops up at final time. Okay, so these are existing approaches with all these names attached to them. Sorry for not reading them to you. Let me now show you our idea, or at least an idea that we followed up on, namely to replace this integer first order derivative by a fractional one. Sorry, there's a t too much. It should be dt alpha u. And so what we do is we replace diffusion by subdiffusion. Okay, so diffusion and subdiffusion, not only because of the name, are closely related from the modeling point of view, so both of them can be seen as limits of continuous time random walks. But the nice thing here is that was the motivation, that it's a method in the context of quasi-reversibility, namely it's causality preserving. Okay, in order to go more into the analysis of this, we need to have more details about Mittag-Leffler functions. So this is just a repetition of the previous slide on fractional derivatives. And here's a repetition of the slide on the Mittag-Leffler function with the bottom line that it satisfies this ODE here. Now some more details about Mittag-Leffler functions. And the important fact that we are going to use here is their asymptotic behavior. So for alpha and beta equal to 1, it's clear how it behaves. It behaves exponential. But look here, there's a distinction, a clear distinction between positive, being in the positive half plane of the complex plane, positive real part half plane, or the negative real part half plane. With positive real part arguments, one actually has super exponential increase because it's 1 over alpha here in the exponent. With negative real part of the argument, we have this sort of power law decay, and it's, if you cut off here at n equal to 1, which will be the case that we are going to use here, it's basically linear, just linear decay instead of exponential one. So if we invert this, instead of the inverse of exponential decay, which will be exponential increase, responsible for exponential ill-posedness, we here have the inverse of this 1 over linear, so it's linear, and then we only have linear increase. So mild ill-posedness. This is just an announcement, so to speak. So in pictures, it looks like this. This is now written down just for real valued arguments, which is actually the case that we are going to look at. What you see here in a log scale is the super exponential increase. So these are several values of alpha. The black line, straight line in a log, semi-log plot is the exponential. And then if you decrease alpha towards 0, then it becomes really fast increase. On the other hand, for negative arguments, it's not a logarithmic plot, so the black line is again the exponential. It really looks like exponential. And then the other lines are the several stages of fractional versions of that Mittag-Leffler function. And you see here that for small arguments, for very negative arguments, it becomes, sort of linear, okay? And that's important. So while the exponential one decreases to 0 very fast, the fractional ones don't. They do decrease, but not as fast. And that's actually the important case for us because we are going to use Mittag-Leffler functions for negative arguments. So just to recall, so what our aim is to replace the diffusion equation by a subdiffusion equation. And now the question arises, well, we have an alpha. In order to get something which is close to this, we will let alpha tend to 1. But the question is, should we do it from the upper or from the lower side? Well, I was already talking about subdiffusion, then it should be from the lower side. The reason for this being is that the convergence of the fractional derivative to the integer one from below is something which is clear from the definition, whereas from above it's also clear, but it's not there, okay? It's not upper semi-continuous, so to speak, so because there's the initial data missing here. Okay, so that's the way to go. We approach one from below. Let me emphasize, since we have been looking at these Mittag-Leffler functions, they are not needed in computations. They are just needed for the analysis. For doing the computations, let me point again to the recent books by Bang Tiyin. He is also in one of the papers. There's much more literature, meanwhile, on numerics for time fractional, also, by the way, for space fractional PDEs. But these are some that I would like to point to. So there's ways to very efficiently simulate numerically solve these types of equations. Whereas we use the Mittag-Leffler functions in the context of a separation of variables ansatz for doing the analysis. Okay, here it goes already. So first of all, for the integer time derivative, first of all, just looking at the ODE version, so again with the parameter lambda. So we have u prime plus lambda u is equal to 0, which is solved clearly by the exponential function. We have this relation between final and initial data. Inverting this gives us this exponential factor. And if you do so in the PDE, meaning that we decompose our elliptic operator plus boundary conditions according to its eigensystem. That's why I wanted to have a symmetric, just for showing, but of course you know much better than me how to deal with the non-symmetric case. Here we just have an eigensystem with real eigenvalues tending to infinity and corresponding eigenfunctions. And then as up here, we have a representation of the searched for initial data in terms of the final data. So we do an expansion in terms of the generalized Fourier coefficients. And this reveals that this jth Fourier coefficient, if we have noise in it, which is naturally the case if we do measurements, this noise gets amplified by this exponential factor. And since these lambda j's tend to infinity, the exponential factor grows unboundedly. That's the reason for exponential ill-posedness of backwards diffusion. Now, if we replace diffusion by subdiffusion, first of all on the level of the ODE, then correspondingly to this first line up here, we get a representation of the initial condition in terms of the final one, dividing by the Mittag-Leffler function evaluated at the final time. So we can also blow this up to a PDE setting, subdiffusion equation and the corresponding representation formula. And then you see it's important to compare this exponential function here with 1 over the Mittag-Leffler function. And since we have seen in the asymptotic result that this 1 over Mittag-Leffler function only increases linearly, we are much better off than up here. But of course we are making an error because we don't look at the original problem, here it is, but at a slightly modified one. Okay, first of all, we can write this in terms of amplification factors. These are these W of lambda j of the Fourier coefficient. So G is our measurement of the final time data. Actually, it will not be G itself. It will just be a noisy version of it. And so we have to take care of this in this coefficient as well. So the amplification factor for, first of all, no regularization will be the exponential one. And this is what we get if we insert noisy data. So we have exact data, which I denote by G here, then what we are actually given is noisy data. And in a bit, we will also look at the smoothed version of this noisy data. So naturally, the noisy data will be rough, so it will be just an L2 function, whereas the exact one, the true one, will be a C infinity function due to the smoothing property of solution of the heat equation. And then at one point, we will also need a smoothed version of this L2 data, which I will denote by G delta tilde. So with this exponentially increasing amplification factor, we can do this, we can certainly not do this for all J. Yes, and if we do want to go back and insert in our representation formula where we sum over all J's here, we cannot do this because this G delta is not the exact data, so there's noise in there which will be exponentially amplified. With a factor that goes to infinity rapidly, so we will be able to do this only for a few J's up to some index k. So we have to truncate our series. That's known as truncated singular value decomposition or spectral cutoff. And that's what is actually the method for comparison. It's known to be an optimal method for inverse problems, optimal in the sense of both stability and approximation error. But you will see fractional subdiffusion gives something better. And well, that's our replacement of dt by dt alpha. So instead of these amplification factors, the exponential ones, we have this 1 over Mittag-Leffler function. So basically linear. But we have to apply, as you will see in a moment, we have to apply this to a smoothed version of our data in order to work out. Okay, just to look at what these amplification factors look like, here's again a log plot of them. And here, so in this log plot, again, the black line, straight line is the exponential function, so the case alpha equal to 1. And we plot these W's as a function of lambda. Yes, because our lambda as being eigenvalues of our elliptic operator, they will increase to infinity. So infinity is at 600 here, but of course it might go beyond. What we see in this picture is that comparing with fractional versions, so the green and the blue one of correspond to the alpha values 0.5 and 0.9. So in some sense, the black one is a limited case of that. What you see here, back here, is the asymptotic behavior, the asymptotic regime, where the green and blue lines are much flatter than the black one. That's nice. However, here in front, the black line is actually even below the blue and green one, meaning that these amplification factors, though they are better in the limit of lambda to infinity, they are worse actually for small values of lambda. And one should take this into account. One can do so by splitting the frequency range. So looking at so that's again the backwards diffusion. So splitting the frequency range in small frequencies. So these are those that are also retained by the full backwards diffusion with truncated SVD, and also doing something on the larger frequencies. So here up here they would just be cut off. Here they are retained with these only linearly growing factors and with this smooth noisy data in them. So to compare what spectral cutoff does with this split frequency subdiffusion, that's, well, we take what we get out of spectral cutoff, that's this upper part here, we sum up to capital K, but we don't throw away the rest. Instead, we use also the rest, the remaining frequency, the high frequencies, and try to get out of them what we can in a stable way. Okay. Again, let me point out that for doing numerical computations, it's now a bit more tricky. We have to project out the lower frequencies and do something more or less explicit. So doing projection on the first few eigen modes. Actually, K in applications or in the examples that we looked at is very small, so that's not that costly. It's about 3 or 4. And then for the rest, after having projected out the low frequencies, we can again go back to numerical PDE solution. Okay, of course this can be continued to splitting into multiple frequency bands, and theory allows this. Also 1D implementation easily allows this, as you will see in my pictures. Well, doing it for a real world problem, I don't know, but at least it's really promising, and in simple example, it pays off to split the frequency bands in more parts where we use different alphas for each part. So for the smallest frequencies, we'll use the largest alpha, the one that is closest to 1, to unity. And then as the frequency increases, we need more stability, so we will use smaller alphas. That's the reasoning behind this. So let me show you how this works in numerical experiments. So here again, the black line is the actual one, the one that the U0 that we are supposed to recover from a backwards diffusion problem. So that's the exact one that we aim for. And here are the split frequency reconstructions. You see here, since the solution has a kink, there's high frequencies involved clearly. And the more refined, so to speak, the process is for reconstruction, the better one can recover also the higher frequencies. This is with relatively small noise. With larger noise, there's another example where we do a comparison with just plain singular value decomposition, truncated singular value decomposition. So taking just K, 3 or 4 frequencies, and then throwing away all the rest. And you see from the black line, there's of course many frequencies involved, and the red dotted line is not really able to capture that. Whereas if we do a bit more, here for example, do a double split of the frequency band, we can follow the black line much more closely, although we have pretty high noise here for an exponential ill-posed problem. Here's an even more spectacular, as we felt, example. We have compared the truncated SVD, basically doing nothing beyond K. That's again the red line that is only able to very costly follow the exact solution with a double and even triple split frequency approach. Okay. A few words about the convergence analysis, or maybe, I don't, yes, just a few words. So going back to that Mittag-Leffler function representation, what we want to do is regularization by using fractional derivatives. So since we want to approach the integer derivative by a fractional one, we want to make the difference between 1 and alpha small, so this is epsilon, and epsilon will tend to 0. So this plays the role of a regularization parameter. So the important result for this purpose is, so there's 2 items. We have to guarantee stability with respect to noise in the data on one hand, and on the other hand, we have to be able to assess the approximation error that we make by replacing 1 with alpha. So here you see the stability estimate, and we are actually going to use the left-hand inequality of these two, because we are taking the reciprocal and want to estimate from above. Using properties of the gamma function, this tells us that 1 over the Mittag-Leffler function, that's just our amplification factor, is proportional to 1 over 1 minus alpha. Times lambda, by the way. So that's this factor lambda is something which we have to take into account further on. What we see is As long as alpha is smaller than 1, we have boundedness here. As alpha approaches 1, this bound gets lost. Clearly, it has to be because we are approaching an ill-posed problem. So to assess the approximation error, we have to estimate the difference between the Mittag-Leffler function and the exponential function, which is the true propagation factor here, in a quantitative way, and that's done here. So again, there's a 1 minus alpha here, but luckily not in the denominator, so this right-hand side goes to 0 linearly as alpha approaches 1. That's how it should be. On top of this, we also have such a boundedness condition, which would be important if I would be able to show you the convergence proof, because it relies on the Lebesgue's dominated integration theorem for exactly this quantity here. So we can also estimate this thing after dividing by the Mittag-Leffler function. Okay. Then it's just bounded. Okay. There's no 1 minus alpha over here, but that's enough for convergence. Okay, now just to repeat, so we have, instead of this exponential instability for the true problem, a stability estimate well, it contains this lambda here. I want to mention this too. I want to show you what the consequences of this factor lambda are, because clearly in this estimate here, that's estimate for fixed lambda, but we have lambda j's that tend to infinity. So there's another factor that tends to infinity in our sum. What does this do? Well, if we look at the L2 norm of our reconstruction from up here, that's this one here, we will be able to bound it as follows. So this is just inserting, so first of all, this is just using Parseval's identity for this L2 norm, so becoming a small L2 norm in terms of the Fourier coefficients, and then, so generalized Fourier coefficients, and then we just insert the formula from up here, this one here. And we estimate this W of lambda j and alpha with this formula here. That's the next step in the inequality. And well, recalling that lambda j is just the eigenvalue corresponding to this eigenfunction phi j, we get that this is just A applied, so our elliptic operator applied to this G tilde delta, which is basically Laplace operator to apply to it. So we need an H2 norm, a finite H2 norm of G tilde delta. That's why we have to do that smoothing. Okay, with this line, at least I was able to show you a little bit of a proof. Okay, and it shows us that we don't have full stability. Full stability would be L2 stability, because we would be given data in L2 only and recover the initial condition also in L2. But at least what we get is H2 over here, basically H2 L2 stability. And this is just inverting, so to say, a finite number, 2 of derivatives, so it's mild ill-posedness. However, the stability constant, as expected, degenerates as alpha tends to 1. Okay. Yes, we have to pre-smooth the data. I don't go into detail about this. Altogether, we get a convergence result like this. And I would like to show you, because that's convergence in the spirit of regularization theory. So the idea behind that is, in principle, a method is a regularization method if for vanishing noise level, so if the noisy data gets closer to the exact one, then also the reconstruction should improve. With a regularization parameter that also depends on the noise level. So the noise level is called delta here. With the smoothing, it becomes a delta tilde. So we have to choose our differentiation order such that it converges to 1 clearly, so that the approximation error vanishes, but also such that the stability estimate stays a stability estimate, so that this one also tends to 0. So it should tend to 1, but not too quickly, so to say. And with that, we really get convergence in the sense of L2 in the norm that we would like to have. So the bottom line is backwards in time fractional diffusion is a regularization method. Oh, I just wanted to skip the proof, not everything else. Sorry. You can relax until I am. Yes, just some remarks. One can also show convergence rates. What I showed you here was just plain convergence without rates. That's typical of inverse problems. But under higher regularity assumptions on the searched for quantity, U0, one can also obtain convergence rates. But it's an exponential ill-posed problem. The rates will just be logarithmic. That's very natural. And one can do the same thing for this split frequency approach. Okay, just a few minutes for the photoacoustic problem, and now it's time for explaining what it's all about. So what we are going to look at, what I showed you on one of the previous slides, and you have seen it flow by me clicking a moment ago. So it's the acoustic part of photoacoustic tomography. So photoacoustic tomography consists of two parts. It's done by shooting a laser at some point, and then the tissue heats up a little bit. At this point, there's thermal expansion, which sends out an acoustic wave, and this acoustic wave is then measured. So the acoustic pressure at the boundary is what we can measure in the sub-problem of interest. And then it's about recovering the source for this acoustic pressure, which by Duhamel's principle transforms, since this laser pulse is modeled as a delta pulse, transforms into an initial condition. So that's why it looked the way we have seen it, as a backwards wave equation, so to speak. Why is fractional damping important in this context? So in the first part of the lecture, I looked at fractional derivatives as a means for regularizing. So the true problem is still an integer derivative problem. Here it's different. So here fractional derivatives are needed for modeling, for properly modeling damping, attenuation in ultrasonics. So that's already well known for many years that in ultrasonics we don't have this strong damping, we also don't have weak damping. It's something in between. The damping depends on the frequency, and the way it depends on the frequency, it's a power law. It's a power of the frequency, basically, what people can measure. Of course, it also depends on which medium we have for where the ultrasound wave propagates. So the exponent of that power law is basically the slope of this line. So we have a dependence on the material, so to speak, on the tissue type, and we have something which is clearly not always 1, but typically below 1, depending on what type of model we look at. So the important piece here is that using fractional derivatives is, of course, nice as a tool, but then if one goes to applied problems, one also has to make sure that one does proper modeling. And here it comes into play by constitutive modeling. So in acoustics, there's two ways of getting in fractional derivatives. That's the relation between pressure and density, or the relation between temperature and heat flux. And actually people, meanwhile, are looking at both effects at the same time. I will just very shortly mention the pressure-density relation here. And this is actually inherited from elasticity, actually viscoelasticity. So people are deriving these fractional laws in analogy to viscoelasticity, which is something which might be more familiar to you. So what we have here are a set of balance laws. So the equation of motion and also the relation between between strain and displacement. So U is the mechanical displacement here. And in order to, so these are always integer derivatives. They cannot be made fractional. But fractional derivatives can come into play in constitutive modeling. So here's the 1D version, because it's simpler to explain, dimensionality of quantities, so we don't have a tensor, just a single scalar stress, sigma here. And the relation between the stress sigma and the strain epsilon, in the most familiar and simple case, it's given by Hooke's law. That's just plain elasticity. But one can also connect stress and strain rate, or a combination of stress and strain rate, and all kinds of combinations. They have different names. And one can go ahead and you look at fractional versions there. So in constitutive modeling, it's allowed to replace integer derivatives by fractional ones. And people have been doing this, and actually this is a general model class that is now more and more used in mechanics. So carrying this over to acoustics, we have different balance laws. We have balance of momentum and of mass. And the relation that we have to, the gap that we have to fill by constitutive modeling is the relation between mass density and pressure. And that, again, that's the place where we can bring in fractional derivatives. I see that my time is over, but this is actually a method. Yes? Is it over, or can I speak? Yes, it's over, yes. But anyway, that's something I really wanted to emphasize. Unfortunately, I cannot show you more because I was too slow. But still, let me thank you for your attention.
Thank you very much for the very interesting and inspiring lecture. For the audience, are there questions or comments?
Thank you very much for the talk. I was very much interested in this last part, actually. So there's quite a difference in the spectral behavior of damped wave equations depending on the strength of this operator D, and you always think maybe strongly damped is nicer, but what's the desirable properties of the damping from your perspective then?
As you say, strong damping is nicer for the forward problem because we have this smoothing property and we have exponential decay and so on and so forth. But for the backwards problem, so the intuition is again the first one, the heat equation. For the backwards problem, it's bad because it's loss of information. The stronger the damping is, the more information gets lost. That's basically the intuition behind that. So the smaller alpha is here, or these alphas and betas in this combined model here, the better it is for solving the inverse problem. But in this example here with photoacoustics, we cannot choose. It's just we have to adapt to what is given by measurements, by experiments, which basically determine these exponents here. That's actually also an inverse problem that I wanted to show you, to determine these fractional exponents. So we are given a certain degree of ill-posedness that is there due to the strength of damping, and then we sort of have to deal with it. That's how it is in photoacoustics.
Thank you very much. If there are further comments or questions, I invite you to ask Professor Kaltenbacher during the coffee break. So thank you again for the lecture.